Welcome, dear 10th standard students. Last video class in numbers and sequence, we discussed the fundamental theorem of arithmetics. Theorem is every composite number can be written uniquely as the product of power of primes. This video class I am going to discuss the modular arithmetic. The modular arithmetic doing an important role in mathematics. Clock is doing very important role in your daily life. Everyone use clocks. One day you have 24 hours, but in your clock only 12 hours. 1 to 12 numbers only you shown. How is it possible to represent the 24 hours of a day in a 12 number format? We use 1 to 12, and after 12 we use 1 inches of 13 and 2 inches of 14 and so on. That is, after 12 we again start from 1, 2, 3 and so on. In this system, the numbers were around 1 to 12. This type of working around after eating some value is called modular arithmetic. In mathematics, modular arithmetic is a system of arithmetic for integers where numbers were around a certain value. Unlike normal arithmetic, modular arithmetic process cyclically. The ideas of modular arithmetic was developed by great German mathematician Carl Friedrich Gauss. He is called as Prince of Mathematicians. Congruence model. Two integers a and b are congruence modulo n if they differ by an integer multiple of n, that a minus b is equal to kn for some integer k. This can also be written as a congruent b mod n. Here a is a number. That number is divided by n, we get the remainder is b. So, written as a congruent b mod n. Here the number n is called modulus. In other way, a congruent b mod n means a minus b is divisible by n. For example, 61 congruent 5 mod 7. Because 61 minus 5 we get 56. 56 is divisible by 7. When a positive integer is divided by n, then the possible remainders are 0, 1, 2 up to n minus 1. When a number is divided by any number, we get the remainder is less than the divisor from 0 to. Connecting Euclidic division lemma and modular arithmetic. Let m and n be integers where m is positive. Then by Euclidic division lemma we can write n is equal to mq plus r. Here n is the dividend, m is the divisor, q is the quotient, r is the remainder. Where r is greater than or equal to 0, lesser than the m, and q is an integer. Instead of writing n is equal to mq plus r, we can use the congruence notation in the following way. We say that n is congruent to r modulo m if n is equal to mq plus r. This is Euclidean division lemma. For some integer q, n is equal to mq plus r. That can be written n minus r is equal to mq. n minus r congruent to mod 0 mod n. n congruent to r mod n. n is the dividend, r is the remainder, m is the divisor. Thus the connection n is equal to mq plus r. Thus Euclidean division lemma can also be written as n congruent or modulo m. Modulo operation. Similar to basic arithmetic operations like addition, subtraction and multiplication performed on numbers, we can think of performing some operation in modulo arithmetic. The following theorem provides the information of doing this. Theorem 5. A, B, C and D are integers and m is the positive integer such that if A congruent B mod m and C congruent D mod m, then A plus C congruent B plus D mod m. Second one, A minus C congruent B minus D mod m. Third one, A into C congruent B into D mod m. If 17 congruent 4 mod 13, when 17 is divided by 13, we get the remainder is 4. 42 congruent 3 mod 13. 42 divided by 13, we get the remainder is 3. 13 into 3, 39. 42 minus 13, we get 3. Then from theorem 5, first addition, A plus C congruent B plus D mod m, using this here. 17 plus 42 is equal to 4 plus 3 mod 13. 17 plus 42, we get 59 congruent 7 mod 13. 59 is divided by 13, we get remainder is 7. 17 minus 42 congruent 4 minus 3 mod 13 minus 25 congruent 1 mod 13. Minus 25 is divided by 13, we get the remainder is 1. 17 into 42 congruent 4 into 3 mod 13. 17 into 42, we get 714 congruent 4 into 3, we get 12 mod 13. 714 is divided by 13, we get the remainder 12. Theorem number 6. If A congruent B mod n multiplied by C in both dividend and remainder, A into C congruent to B into C mod m. A plus or minus C congruent to B plus or minus C mod m for any integer C. Example number 2.11. Find the remainder when 70,004 and 778 is divided by 7. Since 70,000 is divisible by 7, 70,000, when 70,000 is divided by 7, we get the remainder is 0. So you write 70,000 congruent 0 mod 7. Here the given number is more than 4. So add 4 on both sides. Now 70,000 plus 4 is equal to 0 plus 4 mod 7. 70,004 is congruent to 4 mod 7. Therefore the remainder when 70,004 is divided by 7 is 4. 777 is divisible by 7. 777 congruent 0 mod 7. 777 plus 1 is congruent 0 plus 1 mod 7. 778 is the given number congruent 1 mod 7. Therefore, the remainder when 778 is divided by 7 is 1. Example number 2.12. Determine the value of D such that 15 congruent 3 mod D. Here, Given 15 congruent 3 mod d. Here 15 is the dividend, d is the divisor, 3 is the remainder. To find the value of d, 15 congruent 3 mod d. That means 15 minus 3 is equal to kt for some integer k. 15 minus 3, 12. 12 is equal to kt. The d divides 12. The divisor of 12 is 1, 2, 3, 4, 6, 12. But d should be larger than 3. And so the possible value of d are 4, 6 and 12. Example number 2.13. Find the least positive value of x such that 67 plus x congruent 1 mod 4. Second one, 98 congruent x plus 4 mod 5. To solve the first sum, given 67 plus x congruent 1 mod 4. It can return 67 plus x minus 1 is equal to 4n for some integer n. 67 minus 1 we get 66 plus x is equal to 4n. 66 plus x is a multiple of 4. Therefore, the least positive value of x must be 4. Since 68 is the nearest multiple of 4 more than 66. When adding 2 to 66, we get 68. That 68 is divided by 4. So, the value of x is surely 2. Second one, 98 congruent x plus 4 mod 5. It can return 98 minus x plus 4 is equal to 5n for some integer n. That is 98 minus x minus 4 is equal to 5n. 98 minus 4 we get 94. 94 minus x is equal to 5n. 94 minus x is a multiple of 5. Therefore, the least positive value of x must be 4. Since 94 minus 4 is equal to 90 is the nearest multiple of 5 less than 94. So, the value of x is 4. Exercise 2.3, sum number 1. Find the least positive value of x such that 71 congruent to x mod 8. 71 is the dividend, 8 is the divisor, x is the remainder. To find the remainder x, it can return like this: 71 minus x is equal to 8n for some integer n. 71 minus x is a multiple of 8. 71 minus 7 is equal to 64. Is the nearest multiple of 8 less than 71. Therefore, the least positive value of x must be 7. Second sum, 78 plus x congruent to 3 mod 5. Here 78 plus x is the dividend, 5 is the divisor, 3 is the remainder. 78 plus x minus 3 is equal to 5n for some integer n. 78 minus 3, 75 plus x is equal to 5n. 75 plus x is a multiple of 5. 75 is the multiple of 5. Then 75 plus 5 is equal to 80. Is the nearest multiple of 5 more than 75. Therefore, the least positive value of x must be 5. Third one, 89 congruent to x plus 3 mod 4. Here 89 is the dividend, 4 is the divisor, x plus 3 is the remainder. To find x, it can return like this: 89 minus x plus 3 is equal to 4n for some integer n. 89 minus x minus 3 is equal to 4n. 89 minus 3, 86 minus x is equal to 4n. 86 minus x is a multiple of 4. 86 minus 2 is equal to 84 is the nearest multiple of 4 less than 86. Therefore, the least positive value of x must be 2. Fourth sum. 96 congruent to x by 7 mod 5. Here 96 is the dividend, 5 is the divisor, x by 7 is the remainder. To find the value of x, 90 it can written like this. 96 minus x by 7 is equal to 5n. For some integer n, 96 minus x by 7 is a multiple of 5. 96 minus 1, 95 is a multiple of 5. Therefore, the least positive value of x is 7. 7 by 7, 1. Fifth one, 5x congruent to 4 mod 6. Here 5x is the dividend, 6 is the divisor, 4 is the remainder. It can written like this. 5x minus 4 is equal to 6n. n is an integer. 5x minus 4 is multiple of 6. 5 into 2 minus 4. 5 into 2, 10. Minus 4, 10 minus 4, 6. Is a multiple of 6. Therefore, the least positive value of x is 2.